Hello everyone and welcome back. In today's video and the next we are reaching a pivotal milestone. We are going to combine all the mathematical foundations we've covered in our previous sessions. Our focus today is a deep dive into the mean squared error, MSE loss function. More importantly, we're going to develop a graphical intuition for how loss functions behave. Mastering this visual perspective is a game changer when it comes to designing and debugging neural networks. You'll want to stay tuned until the very end, as we'll be connecting the dots between pure math and practical AI. Let's dive in. Let us begin our mathematical exploration of the loss function by first defining our predicted value, denoted as y hat. In basic algebra, a linear relationship is typically represented as y hat equals mx plus c, where m represents the slope and c represents the intercept. However, within the context of machine learning and deep learning, we adopt a more standardized notation to remain consistent with multidimensional models. Specifically, we represent the slope as w1 and the intercept as w0. Consequently, our prediction equation y hat equals w1x plus w0. With this foundation established, we can now examine the expanded form of the mean squared error, MSE equation. Stay focused as we go deep into the mechanics of this equation. Let's look at what we have, our dataset and our loss function. In this equation, n represents the number of data points, which is 5 in our case. We already know the values for x, the bill amount, and y, the tip amount, because they come directly from our data. The real challenge lies with w1 and w0. These are the unknowns. The entire goal of machine learning is to find the most accurate values for w1 and w0 that minimize the error in our predictions. Now let's translate everything we've learned into a formal mathematical optimization problem. This is the standard language of machine learning. We write our goal as arg min over w1 and w0 of loss. Whenever you see arg min, remember, it's just a professional way of asking, what are the best values for w1 and w0 to make the loss as small as possible? By solving this, we find the sweet spot where our model makes the most accurate predictions. Before connecting partial differentiation and gradient descent through graphical intuition, a quick reminder, if you find these insights valuable, please consider sharing and subscribing to support our growing community. To reinforce today's concepts with interactive quizzes and hands-on projects, visit our learning platform at www.wisdomers.in. Now, let's visualize how the math actually works. Let's examine our loss function more closely. As we've established, it is dependent on two unknown parameters, w1 and w0. To visualize the relationship between these variables and the resulting loss, we project the entire function onto a three-dimensional coordinate system. Observe the graph. The x-axis represents w1, the y-axis represents w0, and the z-axis represents the loss. Take a look at our graph. The specific point on our graph represents the minimum loss point, where the loss reaches its lowest possible value. To identify this point, we generally have two paths: direct mathematical calculation or the gradient descent algorithm. While simple equations can be solved analytically, complex equations require the iterative approach of gradient descent. Recalling our earlier foundations, because we are dealing with two unknown parameters, w1 and w0, we must utilize partial differentiation. Our objective is to find for what W1 and W0 the loss is minimum. In our next session, we will conclude our mathematical journey by deriving the final formulas needed to calculate this minimum loss.